All right. It's quarter past, so let's get started. Different setup today, so hopefully everyone can see. Today we're going to talk about test effort assessment. And basically is how do we know that the developers are doing a good job testing the software? Or how do we know generally that we do a good thing on testing our software? So we're going to talk a lot about coverage today, different types of coverage, and different ways we can analyze the coverage and stuff like that. So it's going to be like high and low abstract level today. So we'll see where we get. But it's basically, we want to assess that we do have enough coverage, for example. It's like, yeah, okay, let's go back. So first of all, we should repeat this. Some definition that we did the first lecture I think, if I remember correctly, it was the first lecture. So some definitions. The input domain, that was all the possibilities, all the inputs that we can send to some unit that we were testing or something, some system under test, basically. So, and if you remember, this became tricky quite fast. So if we had like a simple add function, if we just put two regular integers, for example, the input domain became massive really fast, right? You recall? All right, cool. So, and if we wanted to achieve correctness, that means that we need to test all the input domains for it to be super correct, which is kind of impossible really fast. So this is like utopia because we can't run that in a reasonable amount of time. Because when we write our test suite, we want the test suites to be able to, we need to run them locally, first of all. That's usually what we aim for. We should have some unit test suites that we can run locally. And hopefully they should be as correct as possible, or sort of. But if we want to achieve full correctness, then we need to have a huge amount of tests, even for like a simple add function. So this is like, yeah, not going to happen, really. So we need some way of sort of approximate that. So we need to reach a reliability. So reliability is like, how reliable is this program? It's like, how much can I trust it? It's like, how many tests do we need for it to be trustable enough? Sort of. Yeah, and we get a percentage of that sort of. Let's see. So we are back to really simple programs once again, just to demonstrate all the things. And these are a function. There are two functions. They should produce the same result, but they are written in different aspects or different ways. So the same input, same output. So, but what's different is the inside of it. So, and for this, we could do a correctness analysis, right? Because we have at most 4 versions of the input, because it's Boolean input. And we get 2 outputs, basically, either true or false. So in this case, we can make a correct assumption. We can make all the tests. We can write 4 tests and basically covered all the cases. So in this case, we can do it. But like I said, if this would have been an add function instead, then we're screwed. You can't do that in a reasonable time. So what we could do is we could basically randomize which of these test cases that we do. So if let's say that we, for some reason, randomize the first one and the second one. Okay, then we covered all the outputs that we get. So we get 100% reliability for those tests. All the tests that we run produce a correct output, right? So should we, on the other hand, do like this, and we might have a bug here, then now we have 50% reliability. We have one test that fails and one test that passes, correct? So that's how you can think about reliability. So we need to cover as much as possible. And these are the tricky parts. That's the testing part. You need to be creative on how to write the tests enough so you cover all your bases, basically. So that's what we want to do. So you can do this by sort of randomizing the input. That's one way, but it gets tricky because you have to check it. So let's see. So what we instead want to do is, so instead of randomizing like that, so instead of randomizing which test cases to run, we want to basically go back to with the test selection problem. So, and here we try to figure out which test gives us the best reliability score. So and that can be, so our aim goal is so we have all the bugs, basically, right? We want to find many bugs as possible. But if you have a massive input domain, it's tricky to write good tests that find all the bugs, basically. That's why we have customer support. Sort of. So we could do a lot of things. This is, I think we talked about random testing. One lecture, and this is basically this could be an example of that. Basically, we were randomizing it, and but random testing has its drawbacks, basically. So where do our tests come from? Well, we talked about it in the first lecture. We have some sort of requirements, right? Or have you? Are you taking the course software projects, or have you been taking it? You have taken it. Okay, so you have written requirements and stuff like that. Okay, good. So that's basically, usually this is where it starts. We need to figure out what should we test. So we have fuzzy tests or fuzzy needs up here. We have customers that says, okay, I need a program that does this, basically. So these are the needs. They can be quite fuzzy in how they are written, or if they are even written down. Hopefully they are written down, otherwise it becomes very. So we interpret the needs of the customer. We create some sort of features for it. And from these features, we get specifications and use cases. So use cases sort of explains different ways. So this like is a really simple example of what the use case could be. It's like you specify the steps, or you specify what the user wants. In this case, we wanted to restrict the access to the system, so we needed some sort of login, and we also need to let's see. So It's basically credentials in different aspects. You should be able to access certain part of the system, or you should not be able to access certain part of the system. So these are kind of hard. You can test them manually. You can do the manual expectations. You write down, I think I have. So you can write like a manual scenario for this. So here's where the scenarios come in. So you write down the steps. Sorry about that. The steps of the use case. So you follow these steps, you enter this, open this page, enter this data, basically, and those kind of things. So that's where the scenarios comes in. So each use case can have multiple scenarios. It's like if I try to log in without a username, if I try to type a wrong password, and so on and so on. So, and these scenarios are the ones that we try to create the test cases from. So here we have, we don't know exactly the data. And we kind of know what we want to do. We don't necessarily have the data, but here we actually specify the data that we want to put into. And these are the things that we probably can automate. Scenarios are kind of tricky to automate. In certain tools, you can do it. There are like tools called on a kind of high level, like Cucumber and tools like that. But those are kind of tricky to use, or they are. So in order to use Cucumber, for example, you need to create like functions inside the test tool in order to figure out, okay, so if I should access this web page, for example, how do I do that? Okay, I need to write a function inside of that tool in order to access the web page that's spun up as like in the test environment. So they are quite cumbersome to actually use those kind of tools. So, but you can write really cool scenarios for it, but they are also kind of slow to run. So you don't want to run them on your local machine, for example. You can do it, but it usually takes like 10, 15 minutes or something like that. So you have to go get a coffee in the meantime. So this usually the scenarios, if you write scenario testing for on that aspect, you sort of open a web page or like open an application or something like that. So these test cases here are usually like the unit testing that we are more comfortable with. It's like you specify the input data. So you see a scenario here could have multiple test cases. And that's in order to get reliable, as good reliability for that specific scenario. So we need to write multiple tests in order to satisfy this, have a good reliability of that scenario, basically. So, and the test cases, that's where we actually input the data in itself. So we specify certain exact data. Yeah. So that's basically, the test aspects, when we figure out the testing, it comes from the requirements. And usually that's also what we want to verify. I'll get to that in a bit, I think. So yeah, you could, here's an example of like one way to write the scenario. So you usually have like a list of scenarios. If you remember when I talked about my first encounter with testing at SPCS, we got like, at that time, we got a printout basically of like a bunch of papers. They had printed like tables and scenarios and stuff like that. So we had like a bunch of scenarios that we're supposed to do. So it was like start the application. First of all, we needed to install the new version or the test version of the system on our machines. So after that, we needed to log in. We needed to, and then we had certain test scenarios, basically, where we said, okay, go to this part of the program, and basically do this, do this, do this, verify that this happens. So, so we had a bunch of these, basically. So this is like just like the headline of it. So what's it supposed to do? It should be fairly descriptive of what the scenario is about to do. And we usually mark them in that case, in a way like mark them with an identity number, because we want to do, in order to figure out if we cover the requirement, we need to figure out, okay, which test case corresponds to which requirement, right? So this is like, yeah, you can watch, there's a link and read more about the traceability matrix. So we have, for requirement 1, use case, this and this and that. They correspond, they test that particular use case. So we have 3 test cases for that requirement. So, and that could be different aspects of that use case that we test. So, and this kind of reminds, if you're doing assignment 1, part 1, for example, this is, or I think we wanted you to write like a table for both parts. Yeah. So that's kind of thing. Yeah. This has been around for quite some time, I would say. So this is like a way to measure, do we cover, as like requirement coverage, basically. So we can map that, okay, is there a use case that we are not having, that we don't have a test case for? So is there a gap in the table, basically? See, what was the next? Okay, so that was one way. We can do like a table for that. And so, but how do we do this for X unit tests? For example, a test suite, how do we assess them? Any good suggestions? So there are some coverage tools, right? That's one way we can do it. And those are, the unit tests are usually quite small, right? So we have a bunch of them for each class. So we easily can like get good coverage for classes. We will see in certain aspects where we can actually triple over. So coverage too. We can take a look at an example here, for example. Let's see where. So have to show. Let's see. All right, let's take a look at this. So this is pretty old. It's like an old Java library. It's called Yoda time. And so in assignment 2, you're supposed to pick like a project, an open source project, where you can actually go in and take a look at how the testing is done. So let's take a look at how the source code is structured. The testing is here, for example. Probably this. Let's see. So as we can see, there are quite a few tests written for this particular project. Let's see. So we have some mock functions. We have, yeah, that was maybe not the best. Yeah, well, we do have some asserts and stuff like that. As you can see, they have a lot of asserts inside the same test function. This might not be the optimal thing. We wanted our tests to be as small as possible. But sometimes you might want to verify multiple things inside of one test, but try not to do it as much as possible because this is quite massive, right? So we try to check a lot of things here. So yeah. So as you can see, for this library, we have like a massive amount of tests. So, and this becomes tricky quite fast, right? So if you have a massive code base, you have a massive test code base as well. So you have a lot of code to test. So, and you also have a lot of test code, which becomes quite tricky too. So they use a tool called Surefire. Of course, I dropped it. So let's see. So here we can see that they have 4,233 tests. So pretty good, right? And it took 2.1 seconds to run them and 100% success rate. Can we be sure that we test everything here? Can we absolutely be reliable on that? No, probably not. Let's see if we can probably go down into. So for this, for example, we see that we have the 7 tests in this for this class, for example, and stuff like that. So yeah, so coverage tools are very nice. They take a while to get used to. I haven't used Surefire, so I'm not really sure exactly on what all these things are, to be honest. So there are more than one out there. I think that for Java there is one Jacoco, for example. I think that's okay. For example, it's pretty decent. So, but there are others. So, yeah. Let's see what's. So it gets messy quite fast. So having these kind of tools are helpful, but we can't really be 100% sure that we test the right thing because we could have like there's plenty of times where you actually have you change something in the code and you know it should fail something in the test suite, but the test suite still goes green. And so why? So that's a problem. So we could have those kind of situations, and it's not very good to end up in those. Let's see. Let's start this. So yeah. So that leads us to adequate test, measure good enough. So or Swedish lagom, basically. So we need enough tests in order to make sure that we have cover our bases. It's like you want suspenders, you want a belt in order to have it. So Let's see. All right, so let's say if we go back to and the example in the previous slide where we had R equal, for example, we had two different versions of the same program. They did exactly the same thing, right? So if we think of like this, we have all the possible programs in the world. It's like, sure, why not? And then we have some that are reliable for the solution that we have. We could input certain inputs and we get the same result for some programs, for example. So that's a possibility. This is our small correct program, right? So we had some program that was reliable, that could produce the same output basically on the same inputs that we wanted, but they're different in different other aspects basically. So we want to write, so the red line here indicates a test. So we want to write a test that removes these from the equation. So the things that are on the left side of the red line, we want to remove by writing a good test. So we want to constrain the solution space in that aspect. So, and we want to do this to remove these as well, right? And here. So the bottom line here doesn't really connect with the correct space, because it might be in the R equal case, we don't necessarily get this, but this might be as close as we can get. Because if you try to get like 100% code coverage, you need to jump through some really strange hoops in the end in order to do it, because then you might end up having to test certain Java aspects of Java, for example, and then you're out sailing somewhere that you shouldn't be sailing, basically. So this might be as close as possible, but we did remove a bunch of things before. So this, between the red lines here, we managed to remove these cases, right? So we get closer to the correct space as much as possible. But we might end up with some really weird here that might end up being a bug, for example. So we want our test suite to be closing in on the correctness, basically. So that's what we want to do. We want it as close to the correct definition as possible. So we might end up with this. The dotted line here is a test that remove this on the right-hand side, but it misses these cases here. So this and that are, so the dotted line become basically superficial. You don't need it. It's a redundant test, basically. You can remove it because you have a better one that gets closer to the correct one. So you might end up having these kind of tests in your test suites. And that's also one part that we want to figure out, okay, does this do the same thing as this one, for example? Do we test the same thing? And then we might want to remove the redundant testing. It's exactly the same thing when you code, basically. You don't want unnecessary code if you don't need to, right? So you want to slim down your code base as much as possible, but as long as it's still readable. For me, readability is like the number one thing. If it's not readable, it's like you try to make it more readable in that case. So you want to try to slim down your test suite as much as possible, because you want to be as slim as possible. You want it to run quicker. So I watched one of the old recordings, and the Yoda, if you remember the Yoda time, Surefire, it ran for 2.1 seconds. In an older recording from 2023, I think the Yoda time, it ran for 2.8 seconds. So they probably like removed a bunch or slimmed down or tested something different. So I think the number of test cases was still pretty much the same. So they might end up with something that, or machines could have gone faster as well. So that's a possibility. So, but yeah, you want to, so the test suite that we write needs to be taken care of exactly the same as with the code that we write. Usually we get these kind of things if we write the code first and then the tests. Because you try to figure out enough use cases. If you do the TDD style, for example, you write the test first and then you write the code as simple as possible. You usually avoid these. Or it's easy to figure out, okay, yeah, this will actually do the same thing. Because usually if you write one of these, usually it goes green directly, right? So if we have this, and this is the last one we write, it will go green directly because we test all the test cases here, for example. So the solid red line is the better case. We should remove the dotted case if we can. Let's see. All right. So why is that? Thank you. So very formal expression. I will not read it for you. So basically, it's like so we're back to talking about requirements again. So and requirement output behavior and requirement input domain. So for example, here we have like one test case. So the green dot there is a test case. Okay, so which holds for this. If we write, let's see. Okay, yeah. So here we write another test case. It goes, also works fine. So we have a test case, we have another test case, basically. So if we have like if there's like a linear association between the test cases, this might be good enough, basically. So we could probably expect that every test case on this line should probably work-ish, I guess. So, but there are other cases that might look more like this, like the input domain is not linear anymore. It's like, or the output, the correlation between them are not linear. So we might need to write another test case that's on the line, basically. So in these cases, we need to figure out these kind of things. So yeah. Do you follow on this? It's like need to figure out how they are. So writing, if we look at the linear example, we don't need another test down here, for example. It will probably do the exact same thing. But when we have the wavy line, we might need another test case to test in this quadrant here, for example. So just to figure out, okay, do we cover our bases more in this case? So it's a gut feeling in the end, I would say, on these kind of things. Right. Let's see. Okay, we can start. So let's see. What's something? So this is, yeah. I don't think Let's take a look at the next one. All right, so that was requirement, sort of requirement coverage. So we took a look at, here we played around with the requirement. We have an, for each requirement R in R, there's at least one test case that tests the correctness of P. So P is the program. So it's a very formal definition of that. Matur is very formal in its definition in that book. So we look at the requirements, we look at the output and the inputs basically. So this is like the requirement coverage part. If we want to take a look at this works best also. This is more like a black box testing part. We don't know the inside of it. Usually if we look at the requirements and we do some input here, it's not necessary that we know the inside definitions of it. We figure out, okay, we know about the output, so we need to figure out where the tests should lie in that aspect, basically. So, but we don't necessarily know the inside of it. This can be very useful, for example, if you have like an external API or something like that you want to test. So if you write some tests for it and just to verify basically some aspects of it, because you don't know the definition of those, but you might want to have some sort of, if you can have some tests for it, it might be good, because if you install a new version of it, they might change stuff. So it might be nice to have a break, but something that breaks in your test code, but they're also kind of tricky to write. So if we look more at the white box testing or a glass box, sorry for the tongue twister. So here we look at the path instead. So, and what we want to do here is basically, we want to visit all, as much as the paths that we want as possible in the program. So this is more like something you probably used figuring out with the unit test, for example. So if you have an if statement, we want to go into the if statement. We want to, some test case that doesn't touch the if case, going into the if statement in this case. So we want to start with 1, go to 2. We want 1 that goes to 1, 3, 4, 5, for example. And then we want some that goes through the loop as well. Right? So we want to test all the paths in the program in order to figure out, okay, have we covered everything? So that's path coverage, basically. So, and this is usually what we do as a developer. A lot of times this is the thing. We have the test, we have the code. So we need to put it on the test in order to sort of make it break if we change anything in it. Also to verify that we're actually doing the right thing. So most of the time, this is the thing that you sort of figure out about. Okay. So the tricky part here is here, the loop thingy. So there's something called loop coverage. So you want to have, like, if you don't use the loop, is one test case basically, and if you use the loop one time, and if you use the loop many times. So in order to have like loop coverage for this particular thing, it can become quite tricky. So if we take a look at, and especially since this is the do while loop, because we always do one. the definition of a do-while loop is that we always do one execution. So in this case, we need to have, because if we have an x that it's larger than 2, we throw an exception. So if we put a 1, then it becomes 2. So then we don't do, so that should be false, so we should return 2, right? So if we put 1, if we put 0, for example, we get 1 and still, so it goes through the loop. So we need to figure out all these kind of things. So loops is kind of tricky to test in a good way. Nested loops, even worse, because then you have a lot of even more loops to figure out. So nested loops are not very fun to do testing about. So basically, so but yeah, we'll talk about that. All right, so I think we'll take a break there, and when we come back, we will talk a bit about how. All right. So yeah, so before the break, we talked about path coverage. So, and now we're gonna segue into a little bit how coverage tool work. How can we know coverage, basically? So so we're gonna scratch the surface here, because there you can dig pretty deep in this hole, I think. So how does the coverage tool work? Well, it uses something called instrumentation. So what that means is you can, if you want to, you can read the wiki page that we linked here. So basically what we do is we inject code inside the code. So, and so if we have a function like do connect here, for example, in this case, we have like a connection to a MySQL, it looks like, and then a single return of some sort. So if we want to test that this method was run, it's like we do some sort of log method thing. This is probably, some of you probably recognize how to do this. If you try to debug, did my program run here, basically? So you put out like a debug statement. It's the same principle, basically, on how these kind of things work. So we want to check that this function or method was run. So we inject a bit of code inside of it. So that's also super basic on how this works. If we want to check both that it sort of started the method and then that it actually exited the method as well, we can put more than one of these kinds of statements in there. So basically through instrumentation, that's the basic of how these kind of things work. And this is something that we could probably do ourselves if we wanted to, but they do it for us. Yeah. So in this way, we can basically figure out what part of codes were touched when we do different kinds of things. So in this case, here, this is like, what is this? Any suggestions on what it is? Don't look at the code, look at the red and the green parts. What does this mean? What's your first instinct tells you?
It's covered.
Uh-huh. Yeah, that's the basic of it. So in this case, we have something called line coverage. It's like, okay, does our test suite touch this line? So in this case, socket.closed, for example, it's not touched. So we don't have a test case that actually exercise that part of the code, or at least as far as the coverage tool figured. So we want to test as much as possible if we can, but as you remember from previous lectures, certain parts are exceptionally difficult to test, like printout statements and stuff like that. So it can be tricky. So this is one coverage that usually a lot of tools use. I think, let's see if I can. Wait, there it is. Just need to figure out. Give me a minute. I hid it somewhere. No, I thought I had that open, but I don't, apparently. I don't think the Surefire thing that we looked at had that particular thing. No. All right. So, I'm not going to wait. Basic Jacoco, the test coverage tool that we have for Java, for example, you can do these kind of things with. It's fairly simple. So there's one way to do that. So, and usually the main functions are usually not covered at all if you have that, because usually the main functions usually just start the system, right? So we usually don't have like a test coverage case over that. But the other parts of the program, however, we most likely do. So yeah. So this is this can be a good tool to actually use. Okay, have I covered all my bases in the system? And so this is something that I've used on occasion just to verify that I have good coverage of my classes, for example. So this is a pretty good way of doing it. Yeah, types of coverage. So we talked a bit about these kind of things. We talked about the loop, for example. Components is component class method. It's kind of the same. It depends different sizes. Component, it also depends on the language, basically. If you say some languages have modules, some have classes, some don't have classes, some have functions, some have a mix. JavaScript have a mix of classes and functions. So it kind of depends, but we want as good coverage as possible. That's the aim goal. Block statement, for example, is like code line statements that execute together. So, and this can also vary depending on language, on what a statement block looks like. We want to cover as much statements as we want as possible. Yeah, we talked a bit about the loop coverage, for example, that it was kind of tricky. It's kind of tricky if you just have like a regular for loop as well, and stuff like that. So path, well, yeah, the different decision paths basically. So there's a lot of ways of doing this. Let's see if I did. No, that's nothing there. Yeah, this can be a bit interesting. So the link here, I will show you, goes to a page where different types of coverages are explained. And let's see. Can you even see it? Let's see if I can increase it a bit. So yeah, so code coverage analysis, you see there are a lot of statement coverage, decision coverage, multiple condition coverage, for example. Is if you recognized, if you remember the R equal code in the beginning, the first one had something similar to this in structure. So you need to figure out how to test all the cases, have a good coverage of all the bases there. And so you might end up with like a truth table like this in order to figure out, okay, all the paths in order to do that in a good way. So something simple as a logic statement can be tricky to test, especially if it looks like this. You get like a horrendous amount of test cases that you probably need to fill out in order to have a good decision. But we also saw that simple program that we had in the beginning, you just have two basic paths in order to get a decent reliability of it, right? So basically we needed two tests in order to have a reliable. So you need to figure out how this works. So that can be annoying. Let's see. Okay. So that's a pretty interesting page. I won't go through it anymore than that. But it talks about a bunch of different function coverage, call coverage. Yeah, you can have a look. I think it's fairly formal, so it can be tricky to read, but interesting. All right, so I mentioned quite a few times we might end up with code that is hard to reach, right? So, or hard to test in general. So like in this case, for example, we have a loop here that loops through the header statement. So it's difficult to get like a 100% coverage of this because then you have to jump through hoops in order to do that. So these kind of things, loops can be very tricky to get a very good coverage on, depending on how often you need to iterate the loop, right? Okay, if you have, yeah. So since it might iterate a lot of times, so depending on, in this case, we could probably do figuring out a few test cases in order to have the test coverage higher. But then we have to ask us, is that the necessary test coverage? Is that a necessary thing to test? In this case, it's like, it's the HTTP header, for example. So maybe if we verify that the few of the most important parts are there, then we might be fine. So error handling can be tricky. For example, we might end up, I will mention one part first in the path, because so a path, for example, if you have an if statement, and inside of that if statement you have an if statement, because if the first part is true, you can have like let's say if higher than 42 or something like that, or larger than 42, and then inside you have another if statement that checks the same variable and check if it's less than 42, for example. Then you can never reach that part of the code, so it becomes like an unreachable part. So we can have paths that leads nowhere, basically, or you can never enter that path, basically, based on how the code is implemented. So So that's one part. Yeah. Question? No. All right. So that can be tricky. Error handling can also be tricky because you might need to it might be difficult to actually trigger the error in itself. You might need to do a lot of weird things in order to get it to trigger. So it might be something that you have put there because you know you should have it, and then the same thing with the path problem. Basically, you never reach the error code. It never happens. So, but it's still there. You want to test it, but yeah. So previously, I don't know how the newer versions of the unit testing frameworks work. If they fix that, but main functions and stuff like that have been also exceptionally hard to test, for example. Yeah. And like system out print lines, you have to do redirect the streams and stuff like that. I think we did that last time. If I remember correctly, I showed an example on how to redirect the stream, the output stream, basically. So you need to make, in order, if the aim goal is to have like 100% coverage, in the end, you need to do some really strange hoops. It's like, don't even go there. It's like 100% is like an utopia that you probably can't reach. If your program becomes even slightly more difficult than a simple add function, then you probably can't reach 100% in your test coverage. So, but a decent test coverage is what we want. So usually if you go out when you go out in the industry and work in the companies, their test suites most likely don't reach 100%. If they do, then it's amazing in that case, because then you will probably find some really weird tests, I would say. Yeah, so a bit more of what's hard to test. It's like, yeah, file system, databases, API network, stuff like that. Exceptionally difficult. We can try to sort of emulate it through mocks and stubs and stuff like that to get like a decent sort of fail-safe-ish. Databases is one of those things, for example, that it's nice if you can exercise it, but also, I think I mentioned this last lecture. If you want to test the database, you need the database in a certain state, right? Or most likely you need it to be in a certain state. So then you probably need to like destroy every table, recreate the tables, put some data into the tables, and then you can run your tests. So there's a lot of setup configuration that needs to happen if you want to do like a database call. And that could be like, oh, I want to just do an insert test into the database in order to. So then it might be better to actually like mock the database call and say, okay, yeah, we got this with this. So we're fairly certain that this might work. So the same thing with files and stuff like that. So it becomes tricky when you want to put those kind of things under test. So you have to figure out a middle ground. Well, yeah, maybe not so much for us, but if you have like special hardwares that you need, like IoT solutions, Arduino units and stuff like that, it's kind of tricky. This, however, is something that multiple languages, this is something that you might encounter. Certain games, for example, is quite often they write like the user interface in Lua. If you played World of Warcraft, for example, at least the old versions used Lua in order to script the user interface, basically. So if you if you know how to do this, you could actually create a lot of mods and stuff like that. I haven't tried it myself, but did play the game. Regular expression is also something that actually like sort of a language in itself. And it can be exceptionally hard to test. You can test like you usually don't test the regular expression in itself in that case, because then you probably want to extract it out into something, some other tool in order to test that. What we usually do is probably do like a call to the function that calls the regular expression, have like an approximation, like checking, is this a correct email address or something like that, for example. That's usually where you use the regular expressions, I would say. But there are other scripted machines as well. Some company use like their own language in order to make like rules for salary calculations, for example. So then you have a bunch of experts that are more or less experts on writing on the salary aspects, and they write like scripted program in order to, and then we as a programmer basically feed that with input data and something spits out in the other end. So, and yeah, so this can be tricky because you can't really test the scripted, and then you might need another system in order to test that. So, yeah, data-driven code. And this is where we'll like send, for example, a JSON in. You have a JSON file that configures the code in different aspects. So you have to send a bunch of JSON in order to test that in a good way. Becomes, yeah, really weird after all. And then, yeah, iteration, recursive functions, simulations, games, neural nets. There's a lot of things. I don't even have an idea on how they test the LMM, for example. So how do you test an AI that it spits out the right thing? That's a good. I have no idea. Anyone? No. Okay. I think that's probably something interesting to find out. How do you test the LLM in order to do that? Yeah. Yeah. I think I mentioned. Well, I think we did agree that the new versions of JUnit, you could probably do this. You could probably test the private methods. Not all unit test framework have this ability to do that. Private methods are usually tested through the public method that calls the private method. So you get different paths. So inside, if you call a private method inside that, you need different path in order to figure out. So you need to figure out, okay, how is this private method built, and then test it through the public interface in that case. Another way to do it, I think we saw an example of that, would be through dependency injection. So if you have like, let's say this numerical string has some private method, for example, if we have some private method that we can extract out to the numerical string, for example, and have them to become public, then we could test the numerical string in itself, like in a solid unit, which is usually what you want to do, because you want the units to be something kind of small. So if you have a lot of private functions in this social security number class, for example, you might want to extract out like a helper class that you can dependency inject into the other class, because then you can test the public interface of that instead, which is way easier to do. Also, you get like good extraction of responsibilities. So you might want to consider that if your private method gets exceptionally long to use, or a lot of private method, for example. Yeah, we mentioned that. Java, unmockable code, static, Java console. Yeah, so console logs in itself, I don't know if we want to test them. They are kind of hard. So you could test like the toString functions quite easily because that usually generates like a string. That's very easy to verify that's okay. If I have these inputs, we should get that. So the toStrings methods are way easier to test. Let's see. All right, so smoke tests. I think I mentioned usually you do a smoke test when you sort of start your system. You want to verify that okay, I can still. So you deploy a new version of the system. If you want to do a smoke test, for example, you can do like, oh, I log in, I click around in the interface and see if nothing breaks, basically. So that's sort of like a smoke test. Yeah, so we could try to automate it, but if we put that inside, if we do such a test, for example, in our test suite, and that starts to run the system and do a lot of things, for example, we might end up with a very good coverage all of a sudden because we are exercising a lot of things here. So that could be like, so if you want 100% of the code coverage, this might be a way to do it, but it's not very good to do it in that way. So we try to automate like the smoke test in order to exercise the system, basically. But the problem with this is that most likely it doesn't have any asserts in it. It just tries to click around in the function and see if it breaks. That's basically the smoke test. You want to see if it goes kablooey, basically. So if it doesn't, we'll probably, okay, yeah, it's probably working. So that's so if we want that kind of assert or test, we should probably just we can put it in another test suite and run that in that case, because then it doesn't interfere with our unit test suite. So we can have multiple test suites in order to do this. This is not uncommon. It's quite, I would say it's kind of common, because especially if you have like an integration test suite, which is really slow. Like I said, if you use Cucumber, you exercise it through, you open up the web page, you put in some data inside of the inputs, and you actually press the send button in order to verify that the next page that you get is like correct. So these kind of tests are really slow. So you don't want to run them on your local machine, but you might want to run them in like an integrations pipeline, for example, and verify that it works there. Because the pipeline it doesn't matter if it takes 2 hours to run, if you push the new version, for example. So you could probably do something like that inside of that. I haven't seen that myself in particular. So Daniel is more versed in different way of testing than I am. So this is like a complementary negative test. So he has an assert here. Construct should throw when no parameter. This is like a test he wrote. And he has an assert. If he sends null to the die class, for example, it should if we try to run that and it doesn't throw an exception, it should fail, basically. So in this case, if we send null, we get an exception. But if we do the other way around, we don't get an exception, basically. So so we could write these for like construction if we want to do like test constructions in different ways and stuff like that. So which can be kind of tricky to do if you have factory methods. Certain languages have it's kind of tricky to do. All right. Yeah. So now we're getting to more I would say in kind of academia parts. I think I haven't heard of this before. So mutation score is basically we did encounter it if you've done part 1, for example. If you looked at part 1, for example, we've given you a bunch of buggy versions of a program. So this is what we're trying to do actually. It's like we try to inject faulty code to test our test suite in order to see if it breaks. So that's the mutation score. If it has a let's see. So if you have a low mutation score, it's then if you change something in the code, the test suite doesn't break as you expect it to do. So you want a high mutation score. So if you change something inside of your test suite, or if you change something inside of your code that becomes a bug, your test suite should pick it up. So then you have like high mutation score. So that's a way to test your test suite basically in order to figure out these kind of things. So kind of cool. I haven't heard of that before, so that's kind of neat. I think we have something else called, yeah, so this is yeah, kind of silly example, but so if we send a file, this is like a test program, and this is the if you call, this is what we call basically system test. We call this function with that input basically. So this is the function that we call. Certain languages have that ability to call a function in that aspect. So if we have this, we get an exception. If we have this, we get an error basically, and these are here are when we get closer to buggy versions basically in order to do that. So if we have a good test suite, those should fail. But if we don't have a good test suite, they might not pick up the bug basically. So mutation score is a way to sort of exercise your test suite in different ways. Checked coverage is also let's see if I just have to check my notes on this one. Right, yeah. So checked coverage is which instruction affected the assert outcome relies. So this relies on something called dynamic slicing. I have no idea what it is, unfortunately. So, but if you read the paper that's linked, you might get a better feel for it. So basically what we want to do here is to check, does certain things in our program actually do they contribute to the assert or something like that? It's like in this function, for example, the printf statement for doesn't affect the assert at all. So then it's like kind of unnecessary. So it's a way to check if part of your code does have a meaning or actually contribute to the asserts at all. So, and yeah, I will not go into this because so this is a tool that Daniel wrote, and it's a way to take a look. Yeah, I have no idea what these parts means, basically. I think the red parts are bad. So it's kind of difficult to see. You need like introspective of these kind of things. So certain tools can be tricky to use, basically. So, but yeah, if you're interested, take a look at the check coverage, what it means. I would recommend reading the paper in that case. But it's basically figuring out what part of code doesn't like contribute to. So, final thing. Yeah, so if you do TDD, for example, you probably get like a better coverage of your code because you do a lot more testing and you write the test before you write the code. So the code is actually kind of slimmed down as well. So we probably don't have like the checked coverage problems. Basically, we have code that doesn't actually do something that's necessary. So insufficient coverage is a sign of badly designed tests. So which is kind of true in a way, but I would say certain things are hard to test, right? So with TDD, we get better at designing our tests, but we will eventually encounter things that are hard to write TDD test about. So same thing happens there, right? So, but I would say we probably most likely get a way better coverage if we use TDD, for example, because we do it in small incremental steps. Like I mentioned in the beginning, if we write the code first and then we write the test suite after, we might actually have overlapping tests without knowing it. Because we figure out, okay, yeah, I should test this and I should test this. Here we do it in a different way. We do like, okay, what is the next logical step, basically? What push this? What test do I need to write in order to get a failing test in order to move the function or method ahead? So TDD helps you in that direction. So if you write like I do, I don't use TDD very often myself. I usually write the code first and then I write the test later, but I also have, sometimes I get very messy test suites because of it, basically. So, and it's more often than none I have encountered that you have like multiple tests that do the exact same thing. So this can help you get a better test suite or better optimized test suite, I would say. That's pretty much it. I think that's it for today. Any questions? Except on checked coverage, because I found that.
For the percentage of the test coverage, what is like kind of
normal amount of test percentage? I would say, that it varies quite a bit, but somewhere around 90% is it's kind of, if you get 85 to 90%, then you're in a pretty good state. Most companies usually end up around there, I would say 80, 85, up to 90%. But it kind of depends. For the assignment? Oh, okay. Oh, you meant for the assignment? Yeah, 80, 90%. That's kind of good. So is it for the part 2 or part 1? Yeah, then it should be around that for sure, I would say. Yeah, so that's something to aim for. I think some of the buggy versions might be tricky to get, but the correct version should, test coverage for the correct version should be very good. So that's where you should like aim for 80, 90%, I think, at least. So if you can get that, you're home free. Usually that's where you end up in the industry as well, like around those percentage, like I said. difficult to get to 100. You can do it if you have very isolated code, for example, and you can get high coverage for that particular code. For example, in functional programming, for example, you have pure functions where you can get very good coverage because they usually only do some sort of calculations. They don't call out to a file or anything like that because that's a mutation. So it becomes a different aspect. So pure functions are easy to test because you have like a constrained input domain and output domain that you can test quite easily. Yeah.
Console class, are we supposed to test for printing as well, or is that kind of like,
so
like we have a console like UI class?
Okay.
Are we supposed to like test for printing as well?
No.
Okay.
No.
So
Avoid the console log output test, I would say. I don't see a point in that. At least for practicing now. More focus on